Everyone, welcome back to lecture 5, power system. This lecture we're going to talk about electric generator model as well as transformer. Before I start my lecture here, I'm going to recall what we discussed in the last lecture. Let's say we have a balance load over here. So it's a balanced load. This is the neutral point over here, and neutral normally connected to the ground, right? Neutral normally connected to the ground. So I'm going to make a connection here. All right. So now IA, IB, IC, right? So as you know that all the current have for the balance system, all the current have the same magnitude, but angle difference is 120, right? So if I do that, let's say if I add IA, IB, IC, let's say all have 10 amp, and then it will be 0 degree, 10 negative 120 degree, plus 10 negative 240 degree. If you add all of this, you will see that there has a 0 amps. That means for the balance systems, there is no neutral current. So that means your neutral current, if you add all of them, IN, which is basically your neutral current, is 0. But if a system is imbalanced, this is the balance systems. If the system is imbalanced, see what happened. If the system is imbalanced, is it still 0? Let's take a look at that. Imbalanced. So that means I'm gonna keep the magnitude same here. Just will change the angle. So let's say this is negative 15 degree here, plus let's say this is 110 degree here. Let's say plus this is negative 250 degree here. If I now add them, you'll see that there is no 0 anymore. It has a value and also has an angle over here, 42 degree. All right. So this is IN is not 0 anymore. So balance is very important for power system company. If it's balanced, we're not losing any current through the neutral. If it's not balanced, we're going to lose current through the neutrals. This basically going to the drain. That's all. So you're losing current to the neutral. That's why your power system company wants a very balanced system to not to lose any current through the neutral. All right. So let's talk about this lecture. We're going to talk about electric circuit model and also talk about the power transformer. So generator, in power system, we basically use big generators there. Generator has two parts. One is rotor, one is stator. So rotor is the middle part here. This is called rotor. This is rotates. And this is called stator over here. Stator also called armature because it carries current and is the voltage is induced in there, and that we get the connection to the transmission line, right? And this prime mover over here is basically driven by steam turbine, hydro turbine, or gas turbine. So that mechanical power, this is the mechanical power, P mechanical comes in, and from the stator you get the electrical power out. So as you know that you need a time varying flux to produce the current. So if I go back here for a second, so this slot, you can see the slot over here, these slots over here, let me get a different color. These slots over here, these are all current carrying conductor. So this current carrying conductor get the DC current from the shaft. There is an arrangement, I will show you that later. So DC current comes in. So, and when you have a current, you have magnetic flux. You learn in physics 260. When you have a current, you have flux. Then when you rotate this rotor, then you get time varying flux cutting into the stator. That's why you could induce voltage using this equation over here. V is negative N d phi dt. Phi is the flux. So when you rotate them, rotate the rotor, and that flux cutting to the stator becomes time varying flux. That's how you get voltage induction into the stator, that voltage comes out as the generator voltage. But that's what I'm saying over here. All right, so that's all actually discussed over here. So to give a perspective how big they are, you can see that this is the one of the stator, big stator. They're winding a big stator over here. Look at that. They have to do scaffolding over here, and people standing on the scaffolding to do work. So let's compared to the people, you can see how big those machines are. This one is basically 500 megavolt amp rating machines. All right. And also, you see here, this is one of the rotor goes into the stator over here. So you can see the big slot over here. These slots are for the current carrying conductor that carries the DC current. And that DC current produce flux. Then you rotate them. Then you stator gets the time varying flux to produce voltage. So how do you model them? How do you model this big generator? So this is the excitation voltage, as I said before. This is the excitation voltage over here. E is the excitation voltage. But after the excitation, you don't get directly into the terminal. This is the terminal over here. This is the terminal voltage. You need to get past to the coil you have in the generator, right? Stator coil. So this coil has a resistance called armature resistance. Also has reactance, which is called synchronous reactance, XS, RA and XS. So after you pass those things, then you get the terminal voltage. So your excitation voltage is terminal voltage plus losses in the coil. For infinite bus bar, what you call infinite bus bar, like look at the power system. Power system has thousands of generators in different places all over the country, and there's a voltage need to be maintained at the bus, at the grid, right? So that grid voltage cannot be disturbed by the individual generator. Think about that. If you have ocean, the ocean amount of water in the ocean cannot be disturbed by individual river coming into the ocean, right? That's what's same thing over here. So individual generator cannot disturb the grid voltage. That's why if that happens, so magnitude, phase, and frequency cannot be disturbed by individual generator. That is called infinite bus bar. So this bus bar over here, this voltage is predetermined, it's fixed. So you have the generator to come in and connect to that, but this generator just only pump the power in there, cannot disturb the voltage. That means your generator should match the voltage of the grid. So that's called infinite bus bar. And for the infinite bus bar, we also take the RA out of here. So RA is close to zero. Is compared to reactance, resistance is very small. We can say zero. So this is the model for synchronous machine, simplified model. That basically comes to this one here, E V plus J X S I A. So your I RA is not there anymore. All right. So now with that, so remember that we so now there are three different kind of operation it happens. I'm going to draw it over here again. So you have E over here, right? Then this model has both R and S over here. So then you have load over here, right? So so this is basically your terminal voltage V. The current going here is IA. This is RA. This is JXS, right? So now if I have this voltage over here, which is terminal voltage right here, right? Then if this is the current, it's a lagging power factor load. So current is lagging the voltage. So current over here, IA, is lagging the voltage by some angle. Then remember that voltage and current and voltage is the same phase for the resistive load. So this is the resistive drop here, IA, RA. There, so this resistive drop, we call it as RVR or resistance. Let's resistive. So that drop is same as this IA, same in phase. So then your drop in the inductance will make a 90-degree angle over here to the current. So this is your JXSIA. that will make 90 degree angle to the current. So then if we add all three voltage, terminal voltage, drop in the resistance, and drop the inductance, you'll get your excitation voltage. That excitation voltage actually leading the terminal voltage by an angle delta. This is called load angle. We're going to talk about that in a second, load angle. All right. That is for lagging power factor. For unity power factor, there's no angle difference between current and voltage. So they're both in phase over here. And also their IA, RA, this is your IA, RA, drop at the resistance in phase with the current also. Then you have this one here, 90 degree angle for JXSIA. Then you get this over here. Then leading power factor, now your current is leading. So that means your IA, RA also in phase with the current here. So is IA, RA. Then we have 90 degree angle over here for JXSIA. Then you have this. So you can see over here that for lagging power factor, here, EA is greater than V. And for unity power factor is also E is greater than V. For leading power factor here, E is smaller than V. So that is the three different things over here. And also voltage regulation, you can find it by this equation here. No load voltage minus rated voltage over rated voltage times 100% will give you the what is the voltage regulation at the load. So this regulation needs to be around 5%, plus minus 5%. All right, we're going to do this problem in the class. So we're going to wait until we get to the class. So steady state characteristics of the cylindrical rotor over here. So this is the, you have seen this one, this is the power you should get from your generator undisturbed. Doesn't matter what's happening, you should have this power coming out of the generator all the time. And that is what it is be done here. So look at this one generator over here. This generator is operating in your IA. The armature current can go from lagging to leading and always